Hey guys, it's Random Maths Inc. here, and today I've got some new stuff for you. I'm presenting to you Maths and Chemistry. Cue the explosions. So basically in this series I'm going to be discussing, bits of maths and calculations that you would be doing in chemistry. Why? Just because, why not? It might be some help to some people out there. It might not be. Some of you might just be in here for pure enjoyment. I don't know. There's no purpose to this, basically. Now, currently, I've got plans to do these following topics. These are all taken out of the A-level syllabus, alright, just in case you wonder where they all come from. And I might expand on it eventually at the end if I decided maybe I want to do more. I'll expand on it. I'll see what happens, alright. And so in today's episode, it's probably quite sensible to start with the basic stuff. So we're going to start discussing stoichiometry. Let's do it. So before you even get into discussing the stoichiometry, what the f*** is stoichiometry? Well, stoichiometry is derived from two Greek words, stoichion, which means elements, and metron, which means measurements. So literally it would mean measurements of elements. So basically in stoichiometry, we do calculations involving different products and reactants which are, in a certain chemical reaction, and their proportions, how much reactants will give how much products, and etc. Looking at chemical equations such as this one and, seeing what it means, what we can get out of the equation, and how to do calculations of it. But in this episode, we're not actually going to go into discussing the equations and stuff just yet. We have to discuss something else first. We have to discuss about the masses of these atoms and molecules, because obviously the different atoms and molecules will have different masses. In normal day lives, we would use grams to measure mass of stuff, but when we're talking about atoms, which are tiny little thing, we wouldn't use grams because the gram scale is just way too big to measure atoms. It wouldn't make sense. It's like when we're talking about outer space and then astronauts and astronomers realizes that the space is a bit too big to use kilometers, so they have to use a different scale, light years. In chemistry, chemists decide that, alright, atoms are a bit too small to use grams, so we have to use a different scale to see what their masses are. So rather than comparing the masses of these atoms against the kilogram prototype, which is locked underground somewhere, I don't know, we compare these atoms against something else. We compare it against the atoms of carbon-12. Carbon-12 is the most abundant and the most stable isotope of carbon. It's got 6 protons and 6 neutrons in its nucleus. And on this new made-up scale for measuring masses of atoms or molecules, scientists made it so that an atom of carbon-12 will have a mass of 12. There is no units following 12, the mass is just 12. And then the chemists came up with all of these different terms: relative atomic masses, relative isotopic masses, relative molecular masses, relative formula masses, all of these measuring slightly different things, although they all measure it against the same scale, all measuring it against carbon-12. And they all have the scaling so that carbon-12 will always have a mass of 12. Now I'll start with the relative isotopic mass. If two atoms are isotopes, then they would have the same number of protons. They will still be the same elements. However, they would have different number of neutrons in them, and so they would have different isotopic masses, different relative isotopic masses. And the relative isotopic masses basically is just the mass of a certain isotope, an atom of a certain isotope measured against carbon-12, so that carbon-12 has a mass of 12. So something like uranium-238, that's a certain isotope of uranium, and it has got a relative isotopic mass of 238. Now 238 is a number that's relative to the 12 that was defined for the carbon-12. Now of course a certain element can have more than one type of isotope. That's quite common, and they usually all exist in different proportions, in different abundances. And this is where the relative atomic masses come in. Relative atomic masses or AR, basically takes into consideration the relative isotopic masses of the different isotopes and how abundant they are. Relative atomic masses are basically the average of the mass of atoms of a certain element compared to the scale of carbon-12. The AR, the relative atomic masses, are the numbers that you see when you look up the atomic mass of a certain element on the periodic table. And to demonstrate what relative atomic masses are and how you might find them, I'll use chlorine as an example. Now, chlorine mostly exists as two different isotopes, chlorine-35, which exists about 75% of the time, and chlorine-37, which counts for 25% of all the chlorine atoms. Now, to find the relative atomic mass of chlorine, you would have to find the average of chlorine-35 and chlorine-37, considering the abundances of these two isotopes. You can kind of think in a simple way that maybe say there is 100 chlorine atoms, and so 75 will be chlorine-35, 25 will be chlorine-37, and you just kind of work out the average, and you'll find that the average, the answer, comes out to 35.5. That is the relative atomic mass of chlorine. As you can see, the relative atomic mass, the AR, will not always be a whole number. And then we have the relative molecular mass, which, as the name suggests, will be the mass of a molecule of something compared against carbon-12, where carbon-12 has got a mass of 12. And relative formula mass is really similar to relative molecular mass, except you kind of use it on ionic compounds instead. But you kind of almost use it interchangeably. I've never heard anyone using relative formula mass. I didn't know it was different from relative molecular mass until I just looked it up in my chemistry book. I literally have it open here. So now, to find the relative molecular mass, or the MR, of a certain molecule, you have to first see what its formula is, the molecular formula of that compound is. Then once you've done that, you just add up the relative atomic masses of each individual atoms that exist in that molecule. So let me give you an example. So let's say for some reason we want to find the MR of cisplatin, which is some molecule that is used in anti-cancer drugs. But I don't think you really want to know that, do you? So here's what cisplatin looks like, and here is its formula. So what you do is you just basically count how many times each atom of a certain element appears. In cisplatin, there are 1 platinum atom, 2 chlorine atoms, 2 nitrogen atoms, and 6 hydrogen atoms. And then you'd get out your periodic table, look up the AR values for these individual elements. And then to find the MR, you would simply add up all the individual AR of each atom. So for example, there's 1 platinum atom, the AR of platinum is 195.1. So in the first part, you just do 1 times 195.1. Now there's 2 chlorine atoms, the AR of chlorine is 35.5. So the next part, you do 35.5 AR of chlorine times 2, because there's 2 chlorine atoms. And then you do this for the rest of the elements. And then if you do for the rest of the atoms in the molecule of cisplatin, and then add all the values together, you'll find that the MR, the relative molecular mass of cisplatin, is 300.1. So now that we've discussed relative masses of atoms and molecules, it's probably time to talk about moles and Avogadro's constant. Now, the mole is a type of unit, is one of the 7 SI base units, and it's used to measure the amount of substances. Now, a mole is defined so that if you have a mole of a certain substance, then the number of particles in that substance will be the same as the number of atoms in 12 grams of carbon-12. Again, it's always carbon-12 in these types of units. You can think of the mole a bit like a dozen. You know, a dozen means 12. If you have a dozen of eggs, then you have 12 eggs. If you have a mole of eggs, then you have as many eggs as there are atoms in 12 grams of carbon-12. So it's basically just a unit of numbers, like the dozen. Now, the number of atoms in 12 grams of carbon-12 is obviously going to be quite a massive number. And this massive number of atoms in 12 grams of carbon-12 is what we call Avogadro's constant. The official definition for Avogadro's constant is basically the number of atoms in a mole of a substance. The Avogadro's constant has got a symbol Na, and if you want to know more about Avogadro's constant, there's a very good 28-minute video on how it was calculated from the past to the very present. It's a very interesting video, please do check it out. Now, you just have some substance lying around, then you can find the number of moles that is in that amount of substance that's lying around. The number of moles equals to the mass of that substance divided by the relative mass of that substance. So if I say I have 18 grams of water in a glass, then the number of moles of that water in that glass will equal to the mass of the water in the glass, 18, divided by the relative mass of the water, which is 18 if you work it out. And so there will be 1 mole of water in 18 grams of water. And interestingly, 238 grams of uranium-238, which has got an AR of 238, will also be 1 mole. And if you have 2 grams of hydrogen gas, which is a diatomic molecule that has got an MR of 2, then you also have 1 mole of hydrogen gas. So you might be able to see a trend here. It might all be different masses, but they all are 1 mole. This concept of moles and stuff will always appear a lot throughout chemistry, and it will definitely certainly appear in the next episode of Maths and Chemistry. Now, the last bit of this video, I would like to discuss the different types of formulas, chemical formulas in chemistry. I'm mainly going to be talking about empirical and molecular formulas. I mean, of course, if you do organic chemistry, there's even more types of different formulas, you know, skeletal, structural, whatever. But because we're not doing organic chemistry, I'll just skip over that. Now, the molecular formula just simply shows how many of the different types of atoms there are in a molecule of something. So, for example, glucose, there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So the molecular formula for glucose will just simply be C6H12O6. Now, the empirical formula shows the ratio of the different types of atoms that's in a molecule in its simplest form. So for glucose, its molecular formula is C6H12O6. Its empirical formula will be CH2O. It's in the simplest form. It's in simplest numbers. You take all the numbers at the bottom, you divide all by 6 to get its simplest form. What this tells us is that for every carbon atom in the glucose molecules, there will be 2 hydrogen atoms, and for every 2 hydrogen atoms in the glucose molecule, there will be 1 oxygen atom. Just the ratios, nothing but the numbers of molecules or anything. So now if you were given the percentage composition of each element that makes up a certain substance, it's quite simple to work out its empirical formula. And the best way to show how to do this is by giving you an example. So let's say a certain substance X is made up of 85.7% carbon and 14.3% hydrogen. How do we find the empirical formula of that? Now, you have to first understand that these percentages are the percentage of mass. It's not the actual quantity, not percentage quantity of the atoms, it's the percentage of mass that makes up the substance. So you have to turn these values for mass into the value for the quantity, the actual amount of atoms that makes up the substance. So basically you have to try to find the ratio between the moles of each element that makes up that certain substance. So the simple way of dealing with these percentages is, rather than thinking of these numbers as percentages, think of them as mass. Imagine there is 100 grams of this substance X. If there's 100 grams of this substance X, then 85.7 grams of it will be carbon, and then the 14.3% of it will be hydrogen. And since you have masses rather than percentages, you can use these mass to work out how many moles of each element that will make up this 100 grams of substance X. So as we know from earlier, number of moles equals to the mass of that substance divided by the AR. So trying to work it out for carbon, there would be 85.7 grams of carbon in 100 grams of substance X. and the AR of carbon is 12. That's according to the periodic table. We find that in 100 grams of this substance, there will be 7.14 moles of carbon. Undergo something very similar for hydrogen. Number of moles of hydrogen, this substance will equal to the mass of hydrogen, which is 14.7 divided by its AR, which is 1. And that comes out to 14.3 moles. And there we have the ratios between the carbon and hydrogen. We could put this number into the bottom and form the empirical formula like this to show that for every 7.14 molecules of carbon, there'll be 14.3 molecules of hydrogen, but no, we just don't like decimals, and these numbers are far from the simplest form it could be in. So the best solution is to take that 7.14 and divide both answers by it. We divide 7.14 by 7.14 and we get 1. And if we divide 14.3 by 7.14, we get 2. Roughly 2. And so that number, that ratio looks a lot nicer. It shows that for every 1 carbon atom, there will be 2 hydrogen atoms. And that right there forms the empirical formula CH2, which shows that for every 1 carbon atom, there will be 2 hydrogen atoms. And to go from that empirical formula to molecular formula, it's very simple. You just need the molecular mass, the relative molecular mass of the actual molecule. So let's say the MR, the relative molecular mass of the substance X, is 84. So what you would do is you would divide this MR value of substance X by the MR of whatever molecule the empirical formula you just found. The MR of that empirical formula will be 14. 84 divided by 14 is 6. And so basically you take that 6 and you multiply that 6 by every number of atoms in the empirical formula. So rather than having 1 carbon, there will be 6 carbons, and rather than having 2 hydrogen, there will be 12 hydrogen, and that would be the molecular formula. So for substance X, which has an empirical formula of CH2, it has a molecular formula of C6H12. Now, as you can see here, the molecular formula shows nothing about the structure, the actual structure of the molecule. For all we know, this substance X could be a cyclohexane, or it could be any of the hexene. We just do not know because the molecular formula does not tell us anything about what structure it is. And so yeah, that's pretty much it for the first episode of Maths and Chemistry. It's probably a bit lengthy in the first episode, but I promise that in the future will definitely be shorter. I just had loads of stuff to say in this first episode about stoichiometry. And I'll see you again in the next episode of Maths and Chemistry, where we talk about even more stoichiometry, but this time we actually talk about reactions and reaction equations, which is much more interesting than what we talked about this episode. Or hopefully it is.